So atmospheric scientists have figured out a way to effectively equate the impact of a molecule of methane to a molecule of carbon dioxide in terms of their capacity to store heat in the Earth's atmosphere. It's a very important, very complex calculation. And that calculation depends upon the best available atmospheric chemistry. That's science. Science continues to evolve. The more we understand, the more data we have, the better we're able to do that calculation. So I'm going to take you through roughly 16 years of that calculation. Remember, we're trying to figure out, here's a molecule of methane. If we try to find its equivalence in the number of molecules of carbon dioxide that do the same to the Earth's atmosphere, what's that number? So the International Panel on Climate Control, which consists of the best and brightest scientists from around the world, when it convened and issued its 1995 report, said the global warming potential of methane compared to carbon dioxide is a factor of 21. Methane is 21 times more potent as a greenhouse gas than carbon dioxide. And they have to do that calculation over a time horizon. They have to integrate over a period of time because unlike carbon dioxide, which stays in the atmosphere for almost ever, methane doesn't. The life of a methane molecule in the atmosphere is only about 10 years. So they have to have a time horizon. Over what period of time are we comparing methane to carbon dioxide? And 16 years ago, they said, let's compare it over a 100-year horizon. Fast forward to 2007, the IPCC issued its next report, and because of new science, they determined that the global warming potential of methane was not 21 times that of carbon dioxide, it was 25 times. And for the first time, they said, contrary to what John Hanger and Energy in Depth are saying, for the first time, the IPCC said, you know what? We don't have that long. We don't have 100 years. This global climate change thing is happening quicker than we thought it did, so we better be looking not only at a 100-year horizon, which is tremendously optimistic, we should be looking at a shorter horizon, during which period of time we should be doing something about the problem. So let's look at a 20-year horizon. So now if we compare the heating effect, or the heat trapping effect, of a carbon dioxide molecule and a methane molecule, the methane molecule over 20 years is 72 times more potent. Fast forward 2 more years to a paper which appeared again in a very prestigious journal, Science, by Shindell and his colleagues, and they redid the global warming potential calculation and determined that over 100 years, methane is 33 times more effective in trapping heat in the atmosphere than carbon dioxide, and over a 20-year period, it's 105 times more effective. So when my colleagues and I wrote our paper, we chose to use the latest science. Where's the latest science? Is it 1995, is it 2007, or is it 2009? We used the 2009 numbers. Did we use the 100-year number? Yes. Did we use the 20-year number? Yes. You mean you used them both? Yes. Yes, we did. Surprise, surprise to the people at ANGA, who, by the way, didn't read the paper. ANGA and Energy in Depth, I'm getting a little personal here, issued their rebuttal to our paper before they saw the paper. And they based their rebuttal not on the paper as published, but on the paper as originally submitted before review and revision. That's not good science. So, how does methane get into the atmosphere from unconventional gas well drilling or from conventional gas well drilling? Remember the bubbles? It's one way. So during the initial flowback period, frac job occurs, the fracking fluid has to come back, it comes back with gas. Where does the gas go that comes back during the fracking period? Does it go directly into a pipeline to your house? No. There are 2 things that can happen to it. It gets flared or it gets vented. What does flared mean? Burned. How many people here have seen a flare in Pennsylvania? Okay, how many people believe that all the operators in Pennsylvania are flaring all their gas during flowback? No, that's not true. We had the person in charge of all of Shales Marcellus developments give a seminar at Cornell last week. I had a personal meeting with him and I asked him that question. During flowback, what do? He says, Shell will not flare. Corporate policy, Shell does not flare. I said, where does the gas go? He said, I'm not an engineer, I don't know. That's what he said. So it's vented. So if you flare it, you're burning it, and you're creating carbon dioxide. That's bad. But if you vent it, you're venting methane into the atmosphere, and that's worse from a global climate change point of view. Routinely and continuously at the well site, methane is vented and leaked. So during drilling, if you drill through a shallow gas pocket, does that gas go into production? No, it comes up the well and it gets vented. Not even flared, it gets vented. During liquid unloading, this happens mostly in southwestern Pennsylvania, northeastern Pennsylvania, the gas is dry, nearly pipeline ready. You don't have to unload all the liquids, the propanes and the butanes, but if you do have to unload the liquids, there's routine methane venting during that process. It's allowed by law. During gas processing, dehumidification, compression. Is there methane vented from compressor stations? Yes. Is it allowable? Yes. Should it happen? No. Are there technologies to reduce it? Yes. Are all companies and all operators using the latest and best technologies to reduce venting, either purposeful or accidental? No. Should they? Yes. And during transmission, storage, and distribution. So you got to get the gas from the wellhead through a gathering line to some place where it's processed, compressed, then it goes into a transmission line, then it eventually goes to city gate, and eventually it goes into distribution lines to your homes and to industry. What's the average age of the transmission gas pipelines in the United States? 50 years. What's the average age of the distribution pipeline system in the city of Philadelphia, or the city of Pittsburgh, or the city of New York? Cast iron gas mains, do they leak? The guy in charge of all the gas mains and distribution systems in the city of Philadelphia emailed us last week and said, we lose about 3% of our gas. Okay. There was a recent accident in a place called Allentown. Remember that one? That was a distribution leak that resulted in an explosion that killed some people. Okay, so there's leakage in pipelines. Pipelines aren't perfect. So let's quantify the leaks in the vents. So another table. This is conventional gas in this column. This is shale gas, unconventional gas. And our best estimates, I said estimates, based on industry data, I said industry data, for gas loss during drilling and completion in a conventional gas well is less than 1% of the gas over the lifetime of the well. These are all relative to the total production expected from that well. In a shale gas well, close to 2%. And we've been loudly criticized by people saying, are you kidding? What gas company would allow almost 2% of the total production of their well to disappear? That could be $1 million worth of gas. And we say, okay, show us where it went. Show us the data. Show us that you're capturing it. Show us that it's not being emitted during flowback. Tell the guy from Shell who's not flaring it that he's not venting it. Routine leaks in the emissions at the well site, anywhere from 0.3% to 2%. Venting during liquid unloading, emissions during gas processing, and finally, losses through pipelines. And notice in most cases we have an upper bound and a lower bound because we don't really know the answer because the data isn't really good. So as scientists, what do? Do we say, here's the answer? No, we say, here's the best upper bound estimate, here's the lower bound estimate. It's likely that the truth is someplace in between. That's what good scientists do who don't have definitive data. Who has the definitive data? Who knows the answer to this question? The gas industry, okay? We're criticized for using their data, and they say it's really lousy data. Look in the mirror, okay? Give us better data, we'll give you a better answer. But I doubt very much whether the answer is outside these ranges. We doubt that very much. So now let's complete the charts, and I'm going to give you two charts. In our paper, we looked at both the 20-year horizon and the 100-year horizon, just like the IPC says we should. And like other people say we didn't. We did. Read the paper. So let's look at this upper graph first. Again, a bar chart. Blue means carbon dioxide emitted while burning. The narrow red bars are the carbon dioxide and methane emitted during the production. Bulldozer comes, creates a pad, heavy machinery comes in, drill rigs, compressors, hydraulic fracturing pumps, mud pumps. Those are all diesel engines. They're burning diesel. They're emitting carbon dioxide. Okay? So in that using coal or oil or natural gas, conventional or unconventional, so these little narrow bars are additional carbon dioxide emitted by the industrial process They're not negligible, but they're not large. And there are no big differences across the fossil fuel types. Got it so far?